pair of rabbits. I'm not sure if you can read this. So let's see. Man put a pair of rabbits in a cage. During the first month, the rabbits produced no offspring. That's how rabbits are. But each month thereafter produced one new pair of rabbits. One boy and one girl. If each new pair, that's confusing. If each new pair reproduces in the same manner, how many pairs of rabbits will there be at the end of 1 year? This is an old problem posed, in fact, many centuries ago. So let's think about this. How does this go? So initially, the question is how many pairs are there? So initially, how many pairs are there? Initially, there's one pair. Okay. So initially, there's one pair. 1 month later, how many pairs are there? Still one pair, because they didn't have any offspring. Okay. 1 month later, how many pairs are there? There's 2 pairs. Does everybody see why that is? Right. So the old pair, so we're going to call them the baby rabbits and the adult rabbits. At this point, there's one pair. So initially there was a pair of baby rabbits. They couldn't have offspring. But then they became adult rabbits. Now the adult rabbits have offspring, so now there are 2 pair. Now, 1 month later, how many rabbits are there? How many pairs of rabbits? Now, how do you get that? Do baby rabbits produce babies? No. Exactly. The adults do produce babies because they, rabbits. What's the old expression? Anyway. Okay. So exactly. So there's one adult pair of rabbits, they have offspring. The baby pair doesn't. So 1 month later, there will be 3 pair. Now, 1 month later, how many pairs of rabbits will there be? 5. And why is that? 2 adult pairs, 1 baby pair. So those 2 adults give you offspring. And now you have 5 pairs of rabbits. Now if you can keep track of all this in your head, 1 month later, how many pairs of rabbits will there be? And why is that? Right. How can you keep track of how many adult rabbits there are? Yeah. It's right here. So 5 may be the number of current rabbit pairs, but 3 is the number of adult rabbit pairs. And each of those adult rabbit pairs produces a pair of offspring. So in order to get the next number, 3 plus 5 gives you 8. And this is, as the answer, the news has already leaked out. This is the Fibonacci sequence. Okay. Golden ratio is something new we're going to be talking about as well. Okay, so there you go. So, everyone, I hope, recalls about the Fibonacci sequence. So, and by the way, I should say, historically, this rabbit problem is the problem that is attributed for the discovery of the Fibonacci sequence. It is attributed to an Italian from the 13th century whose name was Leonardo Pisano. Fibonacci had to do with this family name, and he's forever known as Fibonacci. Okay. So remember, first of all, here's the Fibonacci sequence, or at least the beginning of it. Remember our notation for Fibonacci numbers is to say Fn is the nth Fibonacci number. So for example, F1 is 1, F2 is 1, and then for example, what is F3? F3 is 2, etc., etc. Now the way we make this definition in general, we can write this down in notation. We say that Fn plus Fn plus 1 equals Fn plus 2. Nth number, nth plus first number, add them together to give you the nth plus second number. It's a mouthful, but I think you get the idea. Okay, so far so good? Okay, so that was a bit about the Fibonacci sequence, which we've already talked about a little bit. Next. Okay. Which of these would you say is the prettiest rectangle, or most pleasing to look at? Okay. So just from you've saved me the trouble of actually doing a show of hands. Most people shouted out pretty quickly the third one. Okay. Now I'm certainly not going to say that everyone feels exactly that way. However, the overwhelming majority say the third one. And there's no right or wrong. I'll just say that this question has been asked in many studies, and overwhelming people always answer the rectangle that you guys answered, the third one. Now, what is special about the third? It so happens that there's something special about the third rectangle. It looks. What does it looks nicer mean? Oh, is that is that what it is? Okay. So forget about the fact of whether or not I can draw without the edges are sharper. Okay. Okay. So let me ask this again. Ignoring the fact of whether or not the lines are straight or curvy and whether or not I can draw, which rectangle has a nicer shape? Okay. Now, I'll just pretend that you all said the third one, because that's what you said before. And what's interesting about the third one is this. If you were to take the rectangle and cut off, if you were to use the short side and make a square and cut off that square, you would be left with a rectangle in the exact same proportions as your original rectangle. So look at the picture. Look at this picture that I've drawn. So now it's standing vertically, but don't let that fool you. If you take the big rectangle and cut off a square in the obvious way, based on how I've drawn it, you get a smaller rectangle. The smaller rectangle is in exactly the same proportions as the original rectangle. It's horizontal instead of vertical, but it's the same proportions. Does that make any sense? Does everybody know what proportions are?
Yeah.
Okay. So, yes, it's proportional but in a smaller scale. That's what proportional means. Does that make sense? Does everybody know what a smaller scale means? Okay. Well, this rectangle, if you shrank it, would be exactly the same as this rectangle. And the way that we formed the smaller rectangle was by cutting off a square. Okay. So this proportion has a very special name. This proportion is called the golden ratio. So, how can we find what this golden ratio is? Well, we can set up an equation based on everything that we just said. So, let's see. The easiest way to do this is to call the sides of the square x. Actually, wait. No, sorry. I want to call the the sides of the square 1. Excuse me. Okay. So let's call this. Let's assume that the sides of the square are 1, and we're going to call the long side of the rectangle x. Now, how long is this side? This is x minus 1. Does that make sense? Whole side is x. You've taken away 1 by cutting out the square. Okay. So what does it mean to be in the same proportion? It means that you can set up a fraction. Or more precisely, you can set up an equation using fractions. So if you look at the big rectangle, what is the proportion of the larger side to the smaller side? The big rectangle. How long is the long side? X. The long side is x. How long is the short side? It's 1, because it's the same as the square. Does everyone understand what I mean when I say big rectangle and small rectangle? Does everyone see where I've labeled 1? Okay. So x over 1. So this is long over short, and this is the big rectangle. And now we're going to write the same thing for the small rectangle. So on the small rectangle, what's the length of the long side? It's 1. What's the length of the short side? It's x minus 1. So, in the way that I've set this up, what I'm saying, these rectangles are in proportion, so these proportions are equal. These fractions are equal. And now we can just solve this. So how do we solve this? So the first thing you do is, I don't like fractions, so I'm going to get rid of the fractions. So I cross multiply. So you cross multiply, you get, just write this. Solve. You get x times x minus 1 equals 1. Now on the left side I can multiply this out. This gives me x squared minus x equals 1. What kind of equation is this? I'm sure you've all seen it before. This is a quadratic equation. How do we solve a quadratic equation? We get one side to be 0. So you get x squared minus x minus 1 equals 0. Now this doesn't factor nicely, so we can use the quadratic formula. So by the quadratic formula, you get, as a reminder, the quadratic formula tells you that x equals negative b plus minus the square root of b squared minus 4ac over 2a. And let me just interject, I don't expect you to remember this for this class, I'm just showing you where the answer comes from. Okay. So b is negative 1, so negative that is 1. You get plus or minus square root of b squared, which is just 1, or 1 squared, minus 4 times a, which is 1, times c, which is negative 1, all divided by 2 times a, and a is 1. So what does this work out to be? 1 plus or minus the square root of 1 squared is 1, and then you get 4 times 1 times 1 is 4, and then that's going to be, you're going to have a negative and a negative, so that's going to become a plus all over 2. So this is 1 plus or minus the square root of 5 divided by 2. Now it turns out that if we take the negative 1, if we do 1 minus the square root of 5, you get a negative number. So we're not interested in the negative number, we're interested in the positive number. So finally we get one plus the square root of 5 over 2. And that's the golden ratio. Now it might be interesting to see, hey, what is this number approximately? So I'll pull up my calculator here and let's see what this works out to be. So this equals 1 plus the square root of 5 divided by 2. And I want a couple more decimal places than that. Oh, about that. Give me more, give me more, give me more. And remember that the square root of 5 is irrational, so of course we could just keep going and going. So, but notice that it's approximately this number, 1.61803 blah blah blah. So I've showed you the Fibonacci sequence, I've showed you the golden ratio. I want to make a couple comments about both of these things. I had mentioned earlier in the course that the Fibonacci sequence was interesting because it appears in lots of places and it has lots of interesting applications. So I showed you the rabbit problem. That one was slightly made up. But now I'm going to show you, and I showed you that because of its historical significance with the Fibonacci sequence. Now I'm going to show you a real problem. A bee family tree. And we're going to see where the Fibonacci sequence magically appears. Okay. How do bees reproduce? This is actually true. A male bee hatches from an unfertilized egg, so it has a mother but no father. Crazy, go figure. A female bee hatches from a fertilized egg, so it has a mother and a father. So how many ancestors does a male bee have 2 generations ago, 3 generations ago, and generations ago? So let's work this out. So first we're going to start with a male bee. I'm just going to put a little M for male. Now, how many parents does a male bee have? Just one. And what is that parent? Yeah, a female. So okay. M equals male, F equals female, which unfortunately is exactly the opposite for mother and father, as I just realized. So let's just keep male and female in mind. So think male, female, male, female, male, female. Okay. Now a female has what sorts of parents? A male and a female. Let's spread this. Male, female. Okay. Now, let's look at that male bee. That male bee has what sorts of parents? Right. Mother, so just a female. And what about the female bee? What sorts of parents? That's right, mother and father, so it has a male parent and a female parent. Now, what about, don't need that. Okay. What about and we just keep doing this. So what about the female bee? How many parents does it have? Two. One of each. So it's got a male and a female. And again, this male we know only has one parent, which is a female. And then this female has two parents, a male and a female. Now, we can keep doing this, but does anybody notice anything strange and amazing? How many, in our original generation, how many bees are there? There's one. Next generation, one. Next generation, two. Next generation, next generation. Guess how many bees will be in the next generation? There you go. So, surprisingly, the Fibonacci sequence shows up in bees' family trees. Okay. So where else? I have some other examples that I wanted to show you. I don't have the pictures with me, unfortunately, so I'll be inserting the pictures into the notes, and then I'll show you next time. They're really awesome pictures, and I want you to have I want you just to enjoy them. Okay. So, but suffice to say for now, the Fibonacci sequence turns up in pine cones, and it turns up in flowers, and it turns up in leaves. And we'll see the lovely picture of those next time. Okay. The golden ratio. Where does the golden ratio show up? It shows up in the human body. Lots of studies have been done, both scientific and artistic, and it turns out that there's a general consensus that the ideal ratio of height to the height of your navel is the golden ratio. Is that on purpose? Is that a coincidence? I don't know. That's a picture. These are all pictures that I want to show you. Fortunately, I don't have them with me. Okay. Sorry? I don't think the golden ratio appeared there specifically. Or maybe it did, I don't know. Oh, they did? Okay. Alright, that's great. The height from the front floor to your navel. Belly button. Yeah. Okay. So, let's just say that the golden ratio appears in a pentagram. Actually, that's an easy picture that I can sketch for you really quickly. So, all right, let me. I'm gonna. You know how wonderful my drawing is. I had a drawing all prepared, but I neglected it. There. Okay. So pentagram looks something like that, and I'm also going to fill in the pentagon that it's included in. Okay. Now again, my awful drawing aside, you're going to have to pretend that all 5 sides of the pentagon are the same length. Okay. And yes, use your imagination. And they're all straight, etc. Okay. Now it turns out that the ratio of this side to this side is the golden ratio. But wait, it gets worse. The ratio of this side to this side, also the golden ratio. But it's not half. It's exactly 1 plus the square root of 5 over 2, or 1.61803. It's exactly that ratio. For a pentagram, yes. What do you mean by always? Oh yeah, that number is the golden ratio. 1 plus the square root of 5 over 2. That's the definition. Was that your question? Okay, yeah. That number is the golden ratio. Well, what do you mean by the answer? That is the golden ratio, right? That's a number. That number has a special name. That special name is the golden ratio. Right. 1 plus the square root of 5 over 2. Okay. Sure. So we'll look at a picture where the golden ratio appears in a Stradivarius violin. The golden ratio appears in the Mona Lisa. Maybe that's what Hugo had read about and was referring to. It appears in the Parthenon. And I really wish I had this picture because it actually appears everywhere in the Parthenon. What is the Parthenon? Well, the Parthenon was designed by Phidias to celebrate Pericles saving Athens during the Trojan War in the 5th century BC. So the Parthenon is this incredibly famous, incredibly obviously old, and many say beautiful structure in Greece, in Athens. And it survives today, sort of. It's slightly ruined. Obviously, the thing is 2,500 years old. And I'll show you the picture next time. But and perhaps when you see the picture, you'll recognize it. It's this old-looking building. It's got columns in front with a triangle on top. You'll see a picture. Okay. So the first letter in Phidias' name is what? He's Greek. So the first letter is, which is called Phi or Phi. So because the golden ratio appears everywhere in the Parthenon, often the letter Phi is used to represent the golden ratio. So sometimes people will just, instead of writing 1 plus square root of 5 over 2, they'll just write Phi. And it comes from Phidias. Okay. Golden ratio also appears in the Cathedral of Chartres, a 13th century from France. I'll show you the picture next time. Show you that next time. Okay. Wish I had those pictures. Okay, anyway. So, Fibonacci sequence and the golden ratio. Is there a connection? No, I'm just pulling. I'm teasing. Yes, of course there's a connection. What is the ratio of consecutive Fibonacci numbers? Now obviously this changes. The first two Fibonacci numbers, 1 and 1, the ratio is 1. Then it's 1 and 2, the ratio is 2. Then it's 2 and 3, and the ratio is 3/2, which is 1.5. But what happens to the ratio as we keep going and keep going and keep going? Next is 3 and 5. So that ratio is 5/3, which is 1.66666. It keeps going. Next is 8 and 5. So the ratio is 8/5, which is, as a decimal, 1.6. I made a little chart. So the next ratio, the next two numbers are it's going to be 13/8. And that ratio works out to 1.625. Do you notice anything? Next ratio is 1.61538 blah blah blah. The next ratio is 1.61904 blah blah blah. Next ratio is 1.617647 blah blah blah. Next ratio, we're pretty far in here. I think this is F10 or so. 1.6181818. This number starting to look familiar. What is it starting to look like? It's starting to look like the golden ratio. So we keep going, we keep going, we keep going. And here I've gone to about the 16th or 17th Fibonacci number. And what is the ratio of two consecutive Fibonacci numbers? 1.618034, and then some other stuff. So up to about 5 places we've got the golden ratio. And it turns out that in fact if you were able to go quote unquote forever, it would be the golden ratio. It gets closer and closer. What the heck do Fibonacci numbers have to do with the golden ratio? Where did that come from? I don't see any rectangles. Well, this is just one of those curious and surprising things that happens in mathematics where things are connected for reasons you don't always see. Okay. Typo. Well, here's another amazing connection between the Fibonacci numbers and the golden ratio. So, to find a Fibonacci number, you have to find all the ones before it, right? Because you add up 2 Fibonacci numbers to get the next one. So if you want to find the 11th Fibonacci number, you have to find everything before it and then add the next, and then add the last 2, right? Wrong. That may be the definition of the Fibonacci numbers, but it turns out there is a formula for any Fibonacci number. And guess what it involves? Amazingly, it involves the golden ratio. Now, to show you how beautiful the formula is, I have initially written out the formula just using the letter phi for the golden ratio. And then I'll also show you what it looks like with the numbers filled in. If you want to find the nth Fibonacci number, it's just this. By the way, I should add, this is fun extra credit material. I don't expect you to know this. So if you were to, I'm sorry, and that's If it's not clear, that's a phi, not a 4. That's a phi. Okay. So that's 1 over square root of 5 times, in parentheses, phi to the n minus negative 1 over phi to the n. So if you were to write it with numbers and you simplified it a little bit, it would look like this. Now you might say, but Fibonacci numbers, they're all whole numbers. How can I have phis and golden ratios and radical 5s? How can that be? Yeah. It turns out that everything just simplifies unbelievably nicely. So just to give you a quick little example of how this would work, let's find the 5th Fibonacci number using this trick. So it should equal 1 divided by the square root of 5 times, in parenthesis, let's see, actually I'm going to do this a little easier. I'm going to type into this cell the golden ratio, and then I'm just going to refer to it. So the golden ratio, remember, is 1, actually the golden ratio is right here. Okay, so what I'm going to do is 1 divided by the square root of 5 times, now remember, so I'm going to use the original formula. It's the golden ratio, which is this number raised to the, in this case, 5th power, minus, in parentheses, negative negative 1 divided by the golden ratio, which again is this number, all raised to the n power. In this case, I'm doing the 5th Fibonacci number, so it's 5. Close parenthesis. Now, does everyone see how I use the cell reference to reference the golden ratio? So in the spreadsheet it said A1, and A1 is this number, which was the golden ratio. Okay. So there's no way that you would think with all these radicals and 1.618 that you would get an integer. It's 5. And indeed, what is the 5th Fibonacci number? 1, 1, 2, 3, 5. Mathemagic. Okay. So let's see. So I have put here another couple of amazing Fibonacci facts, and these two are simply extra credit. I don't expect you to know these things. They're just extraordinary. It's extraordinary stuff. And it's amazing how Fibonacci sequence, first of all, turns up everywhere. I'll show you the pictures for that next time. And also, there are lots of unbelievable mathematical relationships. What is the sum of the first n Fibonacci numbers? In other words, if you add up 1 plus 1 plus 2 plus 3 plus 5, blah, 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 up to whatever Fibonacci number you want to go to. Close. So Terrell said it's fn plus 1. So you've got the right idea. So really, so you're almost right, and very quickly let me show you exactly where the right answer comes from. So first of all, we know that how do you get every Fibonacci number? It's the sum of the two before. Well, another way to think of this is to say that every Fibonacci number is the same as the difference of the two following Fibonacci numbers. So instead of saying 1 plus 2 equals 3, flip it around. 3 minus 2 gives you 1. And 5 minus 3 gives you 2, etc., etc. Does that make sense? So now we rewrite the sum of Fibonacci numbers using this trick. So the first one we replace as 2 minus 1. The next one is 3 minus 2. The 2 is from 5 minus 3. The 3 is from 8 minus 5. Now what happens when you add all these numbers up? Amazing stuff. What suddenly starts to happen? Cancel, cancel, cancel. For example, in just the terms that I've written down, what cancels? There's a 2 and then there's a minus 2. There's a 3 and then there's a minus 3. There's a 5 and then there's a minus 5. The trick that we've used, everything cancels. Almost everything. So what's left over? So Terrell, your guess from before was Fn minus 1. You were so close. What turns out to be left over is Fn plus 2. And what's also left over is this minus 1 from the beginning, because that doesn't it has no cancellation buddy. So it turns out the sum is the n plus 2 Fibonacci number and then minus 1. So that's very cool. And the next one I'll show you next time, because I also want to show you the picture for it. Okay. So let me very quickly reiterate that a lot of what I wanted to talk about today, I simply wanted to show you a bunch of fun stuff. So regarding what you need to know, for example, for homeworks and exams and such, will basically be the sort of stuff that's on your homework assignment. And you'll see that your homework assignment regarding this material is very straightforward. But I also wanted to take the opportunity to show you a lot of the interesting stuff that can come out with the Fibonacci sequence and the golden ratio. I couldn't resist, just because it's so darn interesting. But consider it all extra credit type stuff that you don't need to quote unquote know for the exam.